Hello, and welcome to QuantPy. In this video, we are going to explain the Ito's definition of stochastic integral with respect to the Brownian motion. This integral can be defined for a much larger class of stochastic processes, the so-called semi-martingales, but we will restrict the scope to the Brownian motion. Ito's integral is one of the most important concepts in stochastic calculus. As you may recall, it is the integral that gives meaning to the symbolic operation of stochastic differentials. For example, we know the Brownian motion paths are not differentiable, but we can still perform manipulations using differentials. This is because the differential gets meaning through the integral. So you can see the integral forms the basis of stochastic calculus. For context, let's quickly discuss the definition of integration from calculus, the so-called Riemann integral, and its generalization, the Stieltjes integral. The discussion will help refresh memory and help understand why these definitions cannot be extended to the Brownian motion. We will start with a concrete example, the function 2 times t squared over the interval from 0 to 2. I am going to ramble on for a couple of minutes about the theory and then try to bring it to life with quick visuals. Now recall that the Riemann's integral is defined as follows. 1 divides the interval from 0 to 2 into n subintervals. Let's represent the partition points of the subintervals by the index t and the set of these points by p. The subintervals that this partition produces are as follows. 1 then defines the lower and upper sums, the story of which goes as follows. We take the minimum and the maximum values that the function takes in each subinterval. We then multiply these values by the length of each subinterval and sum across to get an estimate of the area under the function. These, as the names indicate, provide lower and upper estimates of the integral. We will then need to consider the set of all possible partitions of the interval and calculate the two sums over all these partitions. The greatest of the lower sums will, again, provide lower estimate of the integral, and the least of the upper sums will provide upper estimate of the integral. If the two values coincide, we declare that the integral exists, and the common value becomes the value of the integral. This was far more abstract. The function that we have selected is a very well-behaved function, so we can make the process more concrete. The function is monotonically increasing over the interval of interest, so it attains the minimum value at the left end and the maximum value at the right end of each subinterval. Substituting these into the lower and upper sums formulae, we get, and we can replace the abstract set of all partitions by the limit as n, the number of subintervals, tends to infinity. One can generate the successive partitions in a more clever way by sort of starting with a given partition and then continually refining it, which means you keep the previous partition points and add more points. But as the function we are dealing with here is a nice function, we don't need to worry about these subtleties. Let's see it in action. We plot the function 2 times t squared over the interval 0 to 2. We start with n equals 1. The upper estimate of the area is the value of the function at the right end times the length of the interval 8 times 2, which equals 16. The lower bound is 0 because the minimum value of the function in the interval is 0, so 0 times 2 gives 0. Let's increase n to 2, so we now have 2 subintervals. The upper sum is the sum across the intervals of the value of the function at the right end of each subinterval times the length of each subinterval. So we get 10, which is 8 times 1 plus 2 times 1. The lower sum is 2, which is 0 times 1 plus 2 times 1. We now let n increase. As you can see, the lower sum increases and the upper sum decreases until they both reach 5.33, which is the value of the integral. Let's see how this definition is generalized to the Stieltjes integral. To recap, we wanted to calculate the integral of a function, f, with respect to t, over the interval from a to b. We chose a concrete example, in which we integrated the function 2 times t squared over the interval from 0 to 2. We approached this problem as the limiting sum of the areas of a large number of rectangles which we formed by dividing the integration interval into subintervals, and then setting the height of each rectangle equal to the value that the function takes in that interval and the width equal to the length of the subinterval. Let's introduce some terminology to simplify things. The function f is called the integrand, and t, the integrator. Now the integrand, f, in the above definition can be quite general as long as it is bounded and defined over the interval of integration. We will assume it is continuous. But why restrict the integrator to t? Changing the integrator to a monotonically increasing function generalizes the definition to the so-called Riemann-Stieltjes integral. Monotonically decreasing functions would do as well because they could be transformed into monotonically increasing functions by multiplication by -1. And because any function of bounded variation can be written as the difference of two monotonically increasing functions, the integrator can be any function of bounded variation. The lower and upper sums formulae become. Only the definition of the magnitude of the interval has changed from length to the change in a function. Let's try a concrete example. For consistency with the previous example, let's assume we want to integrate the function f equal t with respect to the function g equal t squared. The interval of integration is the same as before. As we already know the theory, let's skip to the visual. Now, as there are three quantities of interest, t, and the two functions, f and g, we will switch to three-dimensional view. Let's plot the function f, which equals t. The graph of this function will be a 45-degree line in two-dimensional view, but we plot it as a plane to help visualize its interaction with the function g, which we plot in the horizontal plane. Let's highlight the part of the f-plane along the function g. Now, the curved triangular fence, enclosed by the green lines, is the area we need to calculate. We proceed as we did in the Riemann example. We start with one interval and take the upper sum as the value of the function f at the right end of the interval, which we know is 2, and multiply it by the change in the value of the function g, which is along the z-axis, and equals 2 squared, so we get 8. The lower sum is 0, as the function value at the left end of the interval is 0. Now, we can increase the number of intervals to 2, and calculate the upper and lower sums. Notice the intermediate point we inserted is at t squared equal 2, which is 1.4142 in terms of t. Now, as you can see, the upper sum decreases, and the lower sum increases as we increase the number of intervals, until it reaches 5.33, the value of the integral. We can project this into two-dimensional view. All we have to do is to flatten the line tracing the function g to x-axis. So, the integration interval now runs from 0 to 4. Now the function f, which equals t, will grow like square root on the squared scale, and the calculation now becomes very similar to the Riemann example we started with, though the function and the units are different. Now, we should have no problem in visualizing the integral of a function with respect to the Brownian motion. We plot one Brownian motion path in the horizontal plane. In the previous graph, we plotted the function g here, which now get replaced by the new integrator, the Brownian motion. Notice, we have shown the Brownian with frequency of 4 points per unit of t. Let's keep the function f, which we set equal to t. Let's highlight the part of the f-plane along the Brownian path. You can see the Riemann-Stieltjes approach is not going to help due to the very zigzaggy nature of the path. Let's see a couple of steps to make it obvious. As before, the fence enclosed by the green lines is the area we need to calculate, though the fence here has a very rough surface. We proceed as we did in the previous example. We start with one interval and take the upper sum as the value of the function f at the right end of the interval, which we know is 2, and multiply it by the change in the value of the integrator, which is along the z-axis, and is roughly equal to 0, so we get 0. The lower sum is 0, as the function value at the left end of the interval is 0. Now, as we refine the partition, the sums will fluctuate, but how do we show that it converges? And you can see the infinite variation of Brownian motion which manifests itself through the zigzaggy path here makes the Riemann-Stieltjes approach irrelevant. So, a novel approach is needed. Let's refresh the data and the view before we introduce Ito's ideas. For a start, let's replace the function f with a flat line whose height we set equal to, say, the average value of the function. Now, it is trivial to define the integral of this flat line with respect to the Brownian motion. It will just be the height of this plane times the change in the Brownian motion over the interval. Adding more points will not alter this because the height is constant, and the intermediate movements in the Brownian path will sum up to the total net displacement which we have already captured. So, how do we get convergence? Well, we divide the interval into, say, two subintervals, and replace the function with its average value in each subinterval. Calculating the integral in each subinterval is as trivial as in the first step. We just have to perform the calculations twice, because now we have two intervals, and we have to sum them, which again is trivial. You can see where we are going with this. You keep dividing the interval until the approximating function matches the given function and call the limiting value the Ito's integral. Now, you can see that the integral value will change when we refresh the Brownian motion path. Hence, the integral will be a random variable. It is not easy to prove the convergence for each path, so the Ito's integral is usually defined in the mean square sense. Before starting with the formal treatment of Ito's integral, we will quickly recall what mean square convergence requires, and discuss a few related concepts such as inner products and norms, which will help us understand how to measure the magnitude of objects, and how to compare objects in the mean square world. Recall that a sequence x, n, converges to x in the mean square if the following holds. Essentially, the expected value of the squared difference goes to 0 in the limit as n goes to infinity. There is a centuries-old test of convergence which goes by the name Cauchy's criteria. It is very simple and almost obvious and goes as follows. Essentially, we can identify a convergent sequence by comparing the elements of the sequence for large n's. We have seen this theorem in action multiple times. For example, when showing the limit of the Riemann sums, we saw that, when the number of intervals becomes very large, the sums, say, the lower sum, changes very little. And Cauchy just capitalized on that observation to develop his convergence tests. We can use this criteria to modify the mean square convergence criteria. And the cool thing about this is, we can tell whether something converges in the mean square sense, even if we don't know what value does it converge to. Now, if you look at the term inside the limit, you can see that it is just a measure of the distance. And remember, the concept of norm from linear algebra also represents lengths and distances. So we can write the mean square criteria in terms of the norm. Now, we can apply all the concepts from algebra. And, to facilitate that, let's review the relevant concepts quickly. Let's first recall the vectors and the dot products. A more general concept related to the dot product is the inner product. As you may know, the inner product can be defined in many ways, but we will work with the standard version. Of course, in the 2- and 3-dimensional Cartesian space, the dot products and the standard inner product represent the same thing. Adding the inner product to a vector space makes it an inner product space. The inner product naturally leads to a definition of the norm as the square root of the inner product of a vector with itself. The norm can be interpreted as the length of the vector. We can also use this definition to define the proximity of, or distance between, two vectors. And you can see why the inner product spaces are so prevalent. Now, the vector space is a collection of objects which are not restricted to just the Euclidean vectors. For example, we can talk about the vector space of continuous functions over an interval. Two objects in this space could be the functions f and g over the interval 0 to 2. We can define an inner product here, analogously to the Euclidean example. We have just replaced the x and y by the functions and the summation by integration. You may see this as a shift from a finite dimensional space to an infinite dimensional space. And the norm and the distance between two functions can be defined in a similar way. Essentially, the summation becomes integration, but the rest is similar to what we saw before. And we can also talk about the vector space of random variables. The inner product will now have an expectation operator. As expectation is really probability-weighted integration, so we have just added weights to the previous definition. And the norm and the distance definitions are also easily modified. So, now, we have put Euclidean vectors, continuous functions, and random variables on an equal footing. And when you think about it, standard deviation is, now, the same thing as the length of a vector. And the correlation is similar to the cosine of the angle between vectors. Now, let's go back to the Ito's definition. The approximating functions we have been using are called simple functions and are, essentially, step functions, which becomes more obvious in the two-dimensional view. As you can see, the quality of the approximation improves as one increases the number of subintervals. We can write these simple functions mathematically as follows. Or, we can reduce the representation to one line using the indicator functions, which take value of 1 in the subinterval that they indicate and 0 elsewhere. This can, now, be represented as a single term using summation. The approximation works for functions of odd shapes as well. Here is one example. They work for random processes as well. In fact, a theorem in probability that you can find in any standard probability book says exactly what we need. A sequence of simple functions that approaches our random function exists. The function is supposed to satisfy the square integrability condition, which means finite second moment. We have been implicitly assuming this anyway, so nothing changes. The proof is simple and is included in most books, so we are not going to cover it. We will content ourselves with the visual depiction. If the integrand is a random variable, then the c's would be random as well. To avoid the dependence between the integrand and the integrator, complicating the statistical properties of the integral, Ito assumes that the integrand, f, is adapted to the filtration, or is non-anticipating. In simple words, the value of f, at time t, can only depend on the Brownian motion history up to time t, which does seem like a sensible assumption. Imagine being able to trade shares today, with knowledge of their prices in the future. You could end up behind bars, for insider trading or something like that. As the c's approximates f, so they will be adapted to the same filtration. Notice, ci actually represents the value of the simple function in the interval from I-1 to I. So that is why we have used I-1 instead of I. In the subscript of t, if we use I, then we will end up with the complicated dependence we wanted to avoid. And as we saw before, the Ito's integral of a simple function is trivial. So, now, we have a definition of stochastic integral that we can make sense of. With the definition settled, we can now proceed to show the convergence of the integral. Let's summarize the discussion so far. We wanted to define the integral of a function with respect to the Brownian motion. We saw that the Riemann-Stieltjes approach cannot be used. We then discussed a novel idea. We said that the integrand can be approximated using simple functions, which led us to propose a definition of the stochastic integral as the limiting value of a finite sum. We have said nothing about the convergence of the sum yet, so the task ahead is to show that the integral so defined does converge. As you might have anticipated, we are going to work with the mean square in terms of Cauchy's criteria, which we reproduce here for convenience. Plugging in the integral for x, this becomes, we can choose m to be 2 times n without any loss of generality. An advantage of this is that, now, We can think of this as the change in the value of the integral when the number of subintervals is doubled. And we can learn a lot about its behavior from just comparing the first and the second elements of the sequence. Assume that we approximated the integrand using one simple function and we then doubled the number of step functions. We can write the approximating simple functions as follows. Our definition of Ito's integral for the two approximations will then give. We can split the first step function into two, though the function will have the same value in both intervals. We can always relabel the values to give an illusion of them being different. In summary, splitting the step function changes nothing but helps align the summation index of the first approximation to that of the second. So we can now write the difference of the two using the same summation index. We have replaced 1 with n to generalize the result. As the 2 times n is arbitrary, we can change it to n with no impact on anything. So let's reproduce the difference formula in terms of n. Expanding the square and interchanging the expectation and the sum, we get. Now, this expression looks complicated, but we have dealt with a very similar expression in the Ito's lemma video. Let's evaluate them one by one, starting with the first term. This is nothing but the expected value of the square of the sum of a finite sequence. We showed in the Ito's lemma video, using analogy of a square grid and the tower property of expectations, that the square of the sum can be written as follows. Substituting for x, we get. We have just substituted c times the Brownian increment for x. Now, we can take c out of the conditional expectation because it is non-anticipating by assumption. The cross term is 0 because the Brownian increments in disjoint intervals are independent. And we know the expected value of the square of the Brownian increments is equal to the length of the interval, so we get. That's the first term. Done and dusted. Second term is a repeat, so we just replace c with d. Now, let's simplify the third term. Splitting it into the matching indices and non-matching indices terms, we get. Now, the non-matching indices term is 0 because the Brownian motion increments in disjoint intervals are independent. The first term, using iterated expectation and the non-anticipating property of c and d, becomes. And we know the expected value of the square of Brownian increments, so we get. Let's take this to the summary. Now, we can make the substitutions to get. Now the 3 summations are nothing but the Riemann's integrals in the limit, so we can write them in terms of the step functions as follows. Remember, c and the d represent the first and the second step functions. Square and cross terms are not a problem because the intervals are disjoint. And we can now write it as a complete square. This is a remarkable result that we should celebrate. So, let's reproduce it. Let's write the left-hand side in terms of the integral to make the comparison clearer. Combining the two integrals on the left-hand side, this becomes. And you can see that this is, essentially, the Ito's isometry. Might be hard to recognize when written in terms of two integrals, so let's write it in terms of one integral, which is just the continuous version of an earlier result. Let's analyze its implications now. Now, if you recall the earlier discussion regarding inner products, then you can see that both sides are just squared norms. Analogously, we can write the one-variable version as follows. So, essentially, the Ito's integral preserves the distance and the length. Hence, to show that the sequence of integrals of the step functions converges. We just need to show that the sequence of the step functions converges, which is very easy to prove. So we need to prove this statement. Notice we have dropped the square, because the square is not going to change anything here. Let's drop the limits for now. Adding and subtracting the function f, which the step functions are meant to approximate, we get. Now, the triangle inequality gives. All it says is that shortest distance between 2 points is a straight line. And well, the step functions approximate the function f, so both terms should become 0 as the number of steps becomes large. So, the sequence of step functions converges, which by Ito's isometry means that the sequence of the integrals converges. And hence, the Ito's integral converges in the mean square to the integral of a step function, say s. Now, we need to show that the limit is unique. To summarize the previous discussion, we said that a sequence of simple function that approximates our given function exists. We then showed, using Ito's isometry, that the integral of these step functions converges. We have said nothing about the uniqueness of the sequence. So what if there is another sequence that also approximates the function f? Then, depending on which sequence one chooses, the result could be different. So, we just need to prove that both sequences lead to the same result. Of course, we are talking in the mean square sense, so let's write the difference of the two using the norm. And we need to show that this goes to 0 in the limit. Adding and subtracting the nth elements of the two sequences, we get. Rearranging the terms, we get. Now, triangle inequality gives. Now, by the hypothesis, the first two terms are 0 in the limit as n becomes large. Using Ito's isometry, we can get rid of the integrals to get adding and subtracting f. And using the triangle inequality, we get. And, as both sequences approximate the function, both terms are 0, and we conclude that the Ito's definition of the integral produces the same result for both sequences. So, we have to agree that the Ito's definition of a stochastic integral makes sense. The Ito's integral satisfies the usual properties of an integral, but it also has some nice statistical properties, which we are going to explore in a future video. We hope you enjoyed the video, and we look forward to seeing you in the next.